So welcome to part 7 of our module 2 for the topic of strain. So we have here thermal stresses. So it is well known that changes in temperature causes dimensional changes in a body. So if the temperature increases or umiinit yung temperature, the material tends to expand. Okay? Lumalaki yung material natin. But when the temperature drops, our material tends to compact or to compress. Lumiliit yung material natin. Okay? This deformation is isotropic, the same in every direction, and proportional to the temperature change. It follows that the associated strain is called thermal strain. So thermal strain is equivalent to um, alpha times delta T. Okay? Where delta T is the change in the temperature. Where the constant is a material property known as the coefficient of thermal expansion. That is alpha. And T is the temperature change. The coefficient of thermal expansion represents the normal strain caused by 1 degree change in temperature. I repeat, thermal expansion represents the normal strain caused by 1 degree change in temperature. So by convention, delta T is taken to be positive when temperature increases. Pag tumaas yung temperature, it is positive. Pag bumaba yung temperature natin, it is negative. Thus, positive delta T produces positive strain. Ibig sabihin, nag-elongate yung material natin. If it is negative delta T, our strain happens to be negative, therefore, our material is contracting. There is contraction, nagko-compress. Okay? So the units of delta are per degree Celsius in the SI system, per degree Fahrenheit in the US system, and typical values are 23 times 10 raised to negative 6 per degree Celsius, or 13 times 10 raised to negative 6 per degree Fahrenheit. For aluminum, it is aluminum, and for steel, it is 12 times 10 raised to 6 per degree Celsius, or 6.5 times 10 raised to negative 6 degree Fahrenheit. So the deformation due to thermal or due to temperature is equivalent to the thermal strain times the length. And we know that the strain due to temperature is equivalent to alpha times delta T. Therefore, sigma T is equivalent to alpha times delta T. The deformation is permitted to occur freely by using expansion joints or roller supports for structures. Okay? So, because if we do not allow the movement due to thermal expansion or contraction, it might cause a damage to our structure. That's why there is a certain degree of allowance. So, the forces that result from the temperature changes cannot be determined by equilibrium analysis alone. That is, these forces are statically indeterminate. When temperature is involved, equilibrium analysis cannot do it alone. We need to have the help of other method, like the compatibility equation. Okay? So equilibrium, compatibility, and Hooke's law. The only difference here is that we must now include thermal expansion in the analysis of deformation. So the procedure, remove the constraints that prevent the thermal deformation to occur freely. Number 2, apply the forces that are necessarily to restore the specified conditions of constraint. Add the deformations caused by these forces to the sketch that was drawn in the previous step. And lastly, by inspection of the sketch, write the relationship between the normal deformation and the deformations due to the constraint of forces. Okay? So for the part 8, last part for this discussion, it will be handwritten.